Imagine for a moment a visitor from another star system breaking apart just millions of kilometers away from the Sun. This visitor, known as 3IATLAS, is only the third confirmed interstellar object ever detected, and it has unleashed massive jets of material that extend 3 million kilometers, far beyond what any normal comet could generate. Now, an unsettling question arises. Did this object simply fragment, scattering alien material throughout our solar system? Or is there a more deliberate, even intentional action at play here? Could this event involve something alien, something we haven't yet comprehended? Tonight, we delve into the mystery, exploring the science and the extraordinary possibilities that come with it. Even though scientists have assured us there is no threat to Earth, by the end of this analysis, you'll grasp the profound implications this alien visitor could have on our understanding of the universe. Stay with us, because what unfolds next isn't just science, it's something no one was prepared for. Part 1. The Day the Sky Changed. On November 9, 2025, a team of astronomers compiled a series of deep space photographs capturing something that should not have been possible. Stretching out from a single point in the darkness, they observed two enormous jets of material. One of these jets reached roughly 1 million kilometers. The object at the center of this strange phenomenon was named 3IATLAS, and it had just become the most puzzling object in our solar system. To truly understand the scale of this, consider that 3 million kilometers is about 8 times the distance from Earth to the Moon. We are not talking about a tiny puff of gas, but colossal structures so massive that they dwarf planetary distances, originating from what was thought to be a relatively small chunk of ice and rock. When the scientists first observed these images, the immediate question was not just, "What is this?" but "What in the world happened here?" 3IATLAS is only the third confirmed interstellar object to ever pass through our solar system. Think about that. In all of human history, with all our telescopes and sky surveys, we have only confirmed 3 visitors from beyond our cosmic neighborhood. The first was Oumuamua, discovered in 2017, a cigar-shaped mystery that sparked countless debates. The second was Boris, discovered in 2019, which at least behaved like a typical comet. Now, 3IATLAS was discovered on July 1, 2025, by the ATLAS survey team operating in Chile. The moment astronomers traced its trajectory, they knew immediately that this wasn't one of our own. The orbit was hyperbolic, meaning it came from interstellar space, passed by the Sun, and would eventually leave our system forever, never to return. This object wasn't bound to our star like comets and asteroids born here billions of years ago.
It was a visitor from somewhere entirely different, carrying with it the chemical signatures of another stellar neighborhood, another era, and a formation process that we can only guess at. Initial estimates from images taken by the Hubble Space Telescope suggested that the nucleus, or solid core, of 3IATLAS was about 5.6 kilometers across. That's already huge for a comet. For context, Halley's Comet, likely the most famous comet in human history, has a nucleus about 11 kilometers long, though it's less massive overall. But here's where things start to get strange. Other data suggested that 3IATLAS might actually be larger, possibly much larger. The numbers just didn't add up, and that was before anyone realized just how bizarre this object really was. Under typical conditions, and based on the models we use to predict how many interstellar objects should pass through our system, an object of this size should be incredibly rare. We're talking odds so low that detecting one in a human lifetime would be a monumental surprise. Yet here it was, large enough to be visible, bright enough to track, and behaving in ways that forced even the most seasoned astronomers to use terms like unprecedented and inconsistent with known models. Then came the turning point. 3IATLAS reached perihelion, its closest approach to the Sun, around October 29, 2025. Perihelion is when comets typically brighten and become active as solar heat vaporizes their icy surfaces and forms the familiar tails. But what happened to 3IATLAS was unlike anything ever seen before. Shortly after perihelion, astronomers began observing enormous jets and the unusual twin plume structure, accompanied by a series of changes that indicated something far more dramatic had occurred. So here's the pivotal question. What if 3IATLAS didn't just become brighter and more active near the Sun? What if it actually fragmented, breaking apart under the stress of solar heating, tidal forces, and internal gas pressure? What if we were witnessing the wreckage of an interstellar visitor shattered into pieces and spilling its alien material across millions of kilometers of space? If that's true, we've just been handed an extraordinary opportunity. Fragmented material means increased surface area, and more exposed surface means more material available for our telescopes and spectrometers to study. We could be observing the interior composition of an object formed around another star, potentially billions of years ago. Its surface altered by cosmic rays during its eons-long journey through interstellar space. It would be like performing an alien autopsy, but on an object millions of kilometers wide, with us as the detectives trying to piece together the cause of its demise.
What if it's still intact, and those jets, that strange energy and the impossible numbers we're seeing, are the result of something other than ice sublimation? What if we're observing propulsion? What if we're witnessing technology at work? This is still not a mainstream hypothesis. It's not even widely accepted yet. But it's on the table. And it's there because the data doesn't neatly fit into the box labeled normal comet. When your observations push you to consider either a radical rethink of comet physics or the possibility of artificial origins, you find yourself in uncharted territory where science intersects with philosophy and discovery edges into the realm of dread. We care about this because the implications are vast. If 3IATLAS fragmented, we gain unprecedented access to interstellar matter. We refine our models and learn how objects survive their journey between stars. But if it didn't fragment, if something else is driving those jets, we might be looking at the first confirmed technological artifact from beyond our solar system. And if that's true, everything changes. Let's focus on what the telescopes actually observed, because the key lies within the data. After perihelion, astronomers around the world began capturing images of 3IATLAS that looked nothing like a standard comet. The twin jets were certainly the main headline, but there was much more to see. The tail structure continued to shift. Amateur astronomers began posting images showing what looked like plumes, like the object was smoking, ejecting material in irregular bursts rather than the steady outgassing that solar heating typically causes. Then came the color anomaly. Comets generally appear white or slightly yellowish because they reflect sunlight and emit light from glowing gases. But 3IATLAS turned bluer than the sun itself at certain points. Not just a little blue, but measurably, significantly bluer. And the color continued to shift, changing over days and weeks in a way that didn't align neatly with its proximity to the sun or any predictable heating model. It was as though the object was cycling through different modes, different states, almost as if someone or something was flipping switches. Spectroscopy, which splits light into its component wavelengths to identify the chemicals present, revealed even more strangeness. Both the James Webb Space Telescope and the SphereX mission turned their instruments toward 3IATLAS and found that the coma, the gas cloud surrounding the nucleus, was overwhelmingly dominated by carbon dioxide. The ratio they measured was astonishing, about 8 parts carbon dioxide to 1 part water. For context, most comets in our solar system have a much lower ratio, often closer to 1 to 10 or even 1 to 100, where water ice is the dominant volatile substance. Why does that matter? Because it completely alters the energy dynamics of the object.
Carbon dioxide sublimates, that is, turns from solid to gas at different temperatures and rates compared to water ice. It also requires a specific amount of solar energy to drive that sublimation process. When scientists calculated how much carbon dioxide 3IATLAS was emitting, they encountered a problem. To produce the amount of gas they were observing, the object would need an enormous surface area, an area that was far larger than what Hubble images suggested. In other words, the object appeared far too small to generate the amount of carbon dioxide it was releasing. The required surface area seemed to exceed the size of the nucleus. Hubble images had indicated it was about 5.6 kilometers across, but the mass loss calculations pointed to a surface area more fitting for an object roughly 23 kilometers in diameter. The math just didn't add up. Another layer of confusion came from the mass loss rate. Estimates suggested that 3IATLAS was losing approximately 5 billion tons of material per month. Let that sink in for a moment. 5 billion tons every month. The outflow velocity of the gas was around 0.4 kilometers per second, which, while fast, is not absurdly high for sublimating gas. However, the mass loss wasn't steady. Initially, the object was losing material at around 150 kilograms per second. A few weeks later, that figure skyrocketed to 2 million kilograms per second. That's a more than 10,000-fold increase. To explain this kind of acceleration using standard comet physics, scientists would need a power law of about negative 10.5, which is absurdly steep. Most comets follow a much shallower power law, somewhere between -2 and -4. What does this steep power law mean? It means that the object's activity was far more sensitive to its distance from the Sun than any normal comet should be. This could indicate that the composition of the object is radically different or that its structure changed dramatically. Or it could mean that the physics governing the object's behavior isn't just about solar heating. It's a kind of number that forces scientists to stop and reconsider their calculations. If this data is correct, then it suggests something we don't fully understand yet. All of these anomalies, the high carbon dioxide levels, the insufficient surface area, the steep acceleration, the shifting color, and the non-gravitational acceleration paint a picture that refuses to resolve itself neatly. Each anomaly could, in isolation, be explained by stretching the existing models of comets, but taken together, they form a pattern of behavior that is far too strange to simply brush off. Fragmentation could explain some of these phenomena. If 3IATLAS had broken apart near perihelion, the total surface area would have increased dramatically, leading to more gas production, brighter jets, and faster mass loss. The irregular behavior, the varying tail structures, and the appearance of plumes could all be consequences of this fragmentation.
But fragmentation doesn't fully explain the color shifts, the extreme carbon dioxide dominance, or the precise timing of the activity surge. And that gap, that space between what fragmentation explains and what we observe, is where the unsettling possibilities start to creep in. The data is real. The observations are solid. Multiple independent teams using different instruments have recorded the same anomalies. This isn't just a case of bad calibration or a rogue measurement. 3IATLAS is genuinely behaving in ways that challenge the boundaries of our understanding of comet physics. We're standing at the edge, staring into a space where either our models of comets need a complete overhaul, or we're witnessing something entirely different, something that's not a comet at all. Before we can appreciate just how strange 3IATLAS is, we need to establish what normal looks like. Let's set the baseline. A typical comet is essentially a dirty snowball, an irregular collection of ice and rock that formed during the early days of our solar system. As it approaches the Sun, solar radiation heats its surface, causing volatile materials, mostly water ice, to sublime directly from solid to gas. This process creates a hazy cloud called a coma, and the pressure from sunlight and solar wind pushes the gas and dust away from the Sun, forming the characteristic tail. It's a passive process entirely driven by external energy.
The comet doesn't do anything on its own. It just sits there and melts. Typical solar system comets have compositions that reflect their origins. They formed in the cold outer regions of the planetary system, where water ice was abundant. As a result, water is usually the dominant volatile, with smaller amounts of carbon monoxide, carbon dioxide, methane, ammonia, and other simple molecules. When scientists measure the gas coming off these comets, the ratios are predictable. Water leads and everything else follows. The behavior is also predictable. Brightness increases as the comet nears the Sun, and the tail grows and shifts in response to changes in angle to the Sun and the solar wind. There might be occasional outbursts when a pocket of gas vents suddenly, but overall it's a fairly orderly process. Now let's look at 3IATLAS. Carbon dioxide dominates. The ratio is flipped. Instead of water leading the way, we have carbon dioxide at 8 times the abundance of water. This is not just unusual, it's a complete reversal of the normal pattern. It suggests that 3IATLAS formed in a very different environment, one that was either much colder or much richer in carbon dioxide ice than anything in our solar system. Alternatively, it could suggest that the surface of the object has been chemically altered by some process that doesn't occur in our solar system. Then there's the sheer scale of the jets. Most comets produce jets, but they're relatively modest in comparison.
These jets might extend a few thousand to tens of thousands of kilometers. 3IATLAS, however, is producing jets that stretch millions of kilometers. It's like comparing a garden hose to a fire hydrant. No, scratch that. It's like comparing a garden hose to an industrial water cannon mounted on a dam. The volume and velocity of material being expelled are orders of magnitude higher than anything a typical comet can manage. The tail structures are also bizarre. Comets usually have 2 tails, a dust tail and an ion tail. These tails point in roughly predictable directions based on solar wind and radiation pressure. But 3IATLAS has shown multiple tails, changing configurations, and structures that appear and disappear. Its overall morphology has shifted on a day-to-day basis. It's almost as if the object can't decide what kind of tail it wants, or as if multiple processes are competing for control. This behavior is completely out of the ordinary. Here's the nuclear size issue again, and it's central to understanding the gap. If you want to sublimate enough carbon dioxide to create the observed jets in coma, you need a certain amount of surface area exposed to sunlight. The calculations are straightforward. You take the solar flux at the comet's distance, multiply by the surface area, factor in how efficiently carbon dioxide absorbs that energy and sublimates, and you get the expected mass loss rate. When scientists did this math for 3IATLAS, the required surface area implied an object much larger than what Hubble images suggested. Fragmentation offers a potential solution to that paradox. If the nucleus broke into many smaller pieces, each piece would have its own surface area. Add up the surface areas of all the fragments, and you could get the necessary total surface area without needing a single giant nucleus. It's like crushing a boulder into gravel. The total mass stays the same, but the total surface area increases because all those little pieces have their own exteriors. More surface means more sublimation, more gas production, bigger jets, and a more active coma. The hypothesis fits, but does it fit perfectly? Not quite. Fragmentation should produce observable signatures. You should see distinct multiple nuclei, separate sources for the jets. Observers have been looking, but while the data is messy and the object is far away, there's no clear consensus on whether we're seeing one nucleus or many. Some analyses suggest multiple sources, while others suggest a single active core with asymmetric outgassing. The ambiguity is frustrating. Then there's the alternative. What if 3IATLAS isn't behaving like a normal comet because it isn't a normal comet? What if those jets are exhaust? What if the color shifts are thermal signatures from active systems? What if the non-gravitational acceleration is a result of deliberate course correction? This is speculation, of course.
But it's speculation driven by the data's refusal to fit neatly into any natural box. To use an analogy, imagine you see a bird flying overhead. You expect it to flap its wings, glide, and maybe soar on thermals. But what if this bird is glowing blue, shooting fire from its tail, and moving at 300 kilometers per hour in a straight line with no visible means of propulsion? At some point, you stop trying to explain it as a weird bird and start considering that maybe it's not a bird at all. Maybe it's a drone. Maybe it's something built. 3IATLAS is our glowing blue bird. The expectation was that it would be a comet. The observation, however, stretches the definition of comet to the breaking point. Either it's a comet doing things we've never seen a comet do, in which case our models need a major overhaul, or it's something else entirely, in which case our models are fine, but our assumptions about what's out there just got shattered. Let's imagine for a moment, you're a 5-kilometer ball of ice and rock that has spent millions of years drifting through the galaxy. Over this long journey, you've been irradiated by cosmic rays, bombarded by micrometeorites, and chilled to near absolute zero, far longer than human civilization has existed. Now, you're falling toward a star, and that star is pumping energy into you at a rate you've never experienced before. Your surface begins to heat up, and the ice starts to sublimate rapidly. Gas builds up beneath your crust and pressure increases. The tidal forces from the star's gravity begin pulling harder on your near side than your far side. At some point, something has to give. This is the essence of the natural fragmentation hypothesis. Under extreme conditions near perihelion, 3IATLAS could have simply cracked apart. The stress from solar heating, the internal gas pressure from rapidly sublimating volatiles, and the tidal gradient caused by the sun's gravity could combine to exceed the object's structural strength. Comets aren't solid monoliths. They're loosely bound collections of smaller chunks held together by weak gravity and sometimes some ice acting as glue. Apply enough stress, and they break apart. We've seen this happen before. The most famous example is Comet Shoemaker-Levy 9, which broke into at least 21 distinct fragments after passing too close to Jupiter in 1992. Those fragments then collided with Jupiter in 1994, creating spectacular impact scars visible even through small telescopes. Jupiter's tidal forces tore Shoemaker-Levy 9 apart, and while 3IATLAS isn't experiencing Jupiter's gravity, it is dealing with intense solar heating and a close perihelion passage that could produce similar effects. If 3IATLAS broke up, the fragments would spread out along its orbit, creating a long trail of debris. These pieces would separate over time, moving at slightly different speeds due to their varying masses and the different rocket effects from their individual outgassing. You would end up with something resembling a string of pearls, dozens or hundreds of kilometers long at first, eventually stretching to millions of kilometers as the fragments diverge. Each fragment would have its own surface area exposed to sunlight, increasing the total surface area dramatically. More surface means more sublimation, more gas production, larger jets, and a more active coma. The observed surge in activity after perihelion fits perfectly with a fragmentation event that dramatically increased the effective surface area of the object. Avi Loeb, a Harvard astrophysicist and a key voice in the discussion of interstellar objects, suggested in one of his blog posts that 3IATLAS may have fractured into at least 16 pieces. This estimate comes from trying to reconcile the observed activity levels with the required surface area. If the original nucleus was 5.6 kilometers across, its surface area was about 98 square kilometers. To get 16 times more surface area, you would need roughly 16 fragments of similar size, or many smaller ones. The math is approximate, but it provides a sense of the scale. We're not talking about a minor crack. This would be a complete disintegration of the object. What would this mean for Earth and the inner solar system? The good news first, there is no collision threat. 3IATLAS is on a hyperbolic trajectory, meaning it won't intersect Earth's orbit. The object came from interstellar space, swung around the Sun, and is heading back into the galaxy. Even if it fragmented into thousands of pieces, those pieces are all following roughly the same path, and that path doesn't come anywhere near us. The closest approach to Earth is on December 19, 2025, but even then, it will be millions of kilometers away, far beyond any danger zone. However, there's some less good news, though it still doesn't pose a direct threat. Fragmentation produces a lot of dust and small debris. This material will spread out and be pushed around by solar wind and radiation pressure, creating a diffuse cloud along the object's orbit. If Earth happens to pass through a dense part of this cloud, we might see some weak meteor activity, like a faint meteor shower, where small particles burn up harmlessly in the upper atmosphere. Space-based instruments, satellites, and telescopes might experience slightly increased dust impacts, but these would be microscopic particles at most, an annoyance, not a disaster. There could also be interactions with the solar wind. Charged dust particles could affect the local plasma environment, creating small disturbances in the magnetic fields and particle flows near the Sun. Scientists studying solar physics and space weather might notice anomalies in their data, but once again, nothing that would pose any danger to Earth. If 3IATLAS did fragment, we should be able to observe evidence of this in the coming weeks and months.
The tail morphology should continue to evolve as fragments separate and create distinct plumes. High-resolution imaging might reveal multiple nuclei, bright spots where individual fragments are most active. The overall brightness of the object might gradually decrease as the fragments move away from the Sun and their activity decreases. The dust trails would also become more elongated and diffuse. The timeline is critical here. December 19, 2025 marks 3IATLAS's closest approach to Earth, about 90 million kilometers away, roughly 0.6 AU. This will be our best opportunity for high-resolution imaging, spectroscopy, and detailed characterization. If there are fragments, that's when we're most likely to spot them clearly. If the nucleus remains intact, that's when we'll measure its size and shape with the highest accuracy. Telescopes around the world are already gearing up for that date, scheduling observation time and preparing their instruments. It's like waiting for a jury to deliver a verdict. Scenario A, the violent breakup, is the safest scientific interpretation. It doesn't require any new physics or exotic explanations. It simply describes a comet under stress, doing what comets sometimes do. It's a straightforward hypothesis, parsimony, as scientists call it, meaning it explains the observations with the fewest assumptions. But parsimony doesn't guarantee truth. Sometimes the simplest explanation is still wrong. Sometimes reality is stranger than our safe assumptions. Let's now turn to the alternative scenario, one that many scientists are uncomfortable with but cannot be dismissed entirely. What if 3IATLAS did not break apart? What if its nucleus is still intact, holding together despite the extreme conditions near the Sun? What if the jets, the color shifts, and the non-gravitational acceleration are all being produced by something other than passive sublimation? What if we are witnessing propulsion? There are already clues in the data that suggest this possibility. Non-gravitational acceleration means the trajectory of the object is being altered by forces other than gravity. For a comet, the usual explanation for this is the rocket effect. Gas sublimating from the surface of the object shoots off in one direction, pushing the nucleus in the opposite direction, much like a tiny rocket thruster.
This is a normal process for comets, but the magnitude and pattern of the acceleration observed in 3IATLAS don't fit the typical comet profile. The forces are too strong and too coordinated, almost as if something is actively steering the object. Then there's the color shift. The object has turned bluer than the sun itself, meaning it is emitting or reflecting light at shorter wavelengths and higher energies. This is not typical comet behavior. Sublimation produces visible and ultraviolet light from excited gas molecules, but it doesn't cause a systematic shift to a color that is bluer than the solar spectrum.
To achieve this, you would need either a highly unusual chemical composition or an additional energy source, something that is heating or exciting the material beyond what sunlight alone can do. The energy budget problem is also critical. To generate jets as powerful as the ones observed, the exhaust velocity must be far higher than the thermal speeds of sublimating gas. Sublimation can give you velocities on the order of a few hundred meters per second at most, but the jets from 3IATLAS are clocked at around 400 meters per second, which is already on the high end. To explain the observed thrust in non-gravitational acceleration, you would ideally want exhaust velocities in the range of 3 to 50 kilometers per second. This is not sublimation anymore. This is propulsion territory. This is ion thrusters, chemical rockets, or some other active system designed to accelerate material. In one of his blog posts, Avi Loeb bluntly put it, "Houston, we have a problem." The implication is clear. If 3IATLAS is still intact, and if the jets are coming from a single body rather than multiple fragments, the energy required to create those jets exceeds what solar heating alone can provide. We would need another source of energy, something that actively powers the object, like a propulsion system. So what would an actively propelled interstellar craft look like? Imagine a probe designed to travel between stars, equipped with systems to adjust its trajectory, deploy smaller units, and study the environments it passes through. As it approaches a star, it might activate its propulsion system to correct its course, using stored energy or harvesting solar radiation. The jets we're seeing could be exhaust plumes from these systems, directed bursts of ionized gas or plasma. The color shifts could be thermal signatures from the engine turning on and off. The changing tail morphology might be due to different thrusters firing at different times, creating a complex, evolving structure. This is speculation, of course. There's no smoking gun, no radio signals, no clear artifact that would definitively prove this theory. But the possibility exists. The data doesn't fit neatly into our existing models of cometary behavior, and that leaves open the possibility that we're seeing something entirely different. Something that looks more like engineering than natural cometary processes. What would be the key signs to watch for if this object is artificial? First, an intact nucleus. If high-resolution imaging reveals a single coherent body, this would rule out the natural breakup scenario and force us to look for another explanation for the activity. Second, coordinated jets. If the jets are firing in a regular, predictable pattern with precise timing, it suggests control rather than random outgassing. Third, subtle maneuvers. If the object's trajectory shows small, deliberate changes that can't be explained by gravitational interactions or outgassing, that would be a major red flag. You'd also want to look for periodic patterns in its activity. Does the object brighten and dim in regular cycles? Does the color shift repeat in predictable ways? Does the activity surge at certain distances or alignments? Natural processes can produce periodicity, such as a rotating nucleus exposing different areas to sunlight, but artificial systems might have different signatures and rhythms. It's essential to rule out natural explanations first, but the possibility of something engineered cannot be completely disregarded. Then, there's the question of communication. If this is a probe, would it be transmitting? Would it be listening? Efforts to search for signals from 3IATLAS have so far turned up nothing, but the absence of evidence isn't evidence of absence. Perhaps it's dormant.
Perhaps it uses frequencies or modulations that we're not monitoring. Perhaps it was designed to be silent. Or maybe it's just a rock, and we're reading patterns into random data, projecting agency where none exists. The philosophical stakes are enormous. If 3IATLAS is technology, if it's artificial, then we are not alone. We have had our first confirmed contact with something built by someone else. That would change everything: how we see ourselves, our place in the galaxy, and our future. It would raise questions about intention. Why is it here? Is it observing us? Is it passing through by chance or design? And if it's designed, what does that say about whoever designed it? Even entertaining this possibility feels risky, like crossing a line between science and science fiction. But science has crossed that line before and found reality on the other side. When quasars were first discovered, some astronomers considered the possibility that they were artificial beacons created by advanced civilizations. They weren't, but the question was worth asking. Similarly, when regular radio pulses were detected, astronomers initially called them LGM-1 for little green men. It turned out they were coming from a neutron star, but the speculation was valid at the time based on the data. 3IATLAS could be the same. It could turn out to be just an odd comet, but the data is strange enough, the anomalies numerous enough, that we can't simply ignore the possibility of artificial origins. Now, let's delve into the composition of 3IATLAS, because the chemistry of this object is as strange as its behavior, perhaps even stranger. When the James Webb Space Telescope pointed its infrared instruments at the coma of the object, the spectra that came back were unlike anything from a typical solar system comet. As mentioned earlier, the carbon dioxide to water ratio was around 8:1, extremely high. But as we look deeper, the mystery intensifies.
SphereX, another space-based observatory, confirmed these findings and added more detail. The coma of 3IATLAS was bright in carbon dioxide emissions, glowing intensely in the infrared wavelengths where carbon dioxide molecules radiate after being excited by sunlight. Water and carbon monoxide, two other common volatiles in comets, were barely detectable. The production rates for both were orders of magnitude lower than for carbon dioxide. It's as though this object is made of dry ice with just a trace of frost. Polarimetry, a technique that measures how light is polarized after reflecting off or scattering through a material, provided another layer of insight. 3IATLAS showed an exceptionally deep negative polarization branch, hitting a value of negative 2.7% at a phase angle of 7 degrees. For those not familiar with the term, negative polarization branches are rare and usually indicate very specific grain sizes and compositions in the dust and gas surrounding the object. The value measured for 3IATLAS is unprecedented among comets and asteroids. It doesn't match anything in our catalog of objects. So what does all this tell us? The high abundance of carbon dioxide suggests that 3IATLAS formed in a region of its parent protoplanetary disk where carbon dioxide ice was more stable than water ice, something that typically occurs in the outer regions beyond Neptune, where temperatures drop low enough for carbon dioxide to remain solid while water ice is still abundant. For carbon dioxide to dominate, the formation region would have had to be even colder, or it might have had a different chemical mix, one enriched in carbon and oxygen but depleted in hydrogen. This points to an environment far from its original star, or perhaps around a star with a composition different from our Sun. There's also the cosmic ray hypothesis. Over millions of years of interstellar travel, an object like 3IATLAS would be bombarded by galactic cosmic rays, high-energy particles that permeate the galaxy. These particles can penetrate several meters into ice and rock, breaking chemical bonds and creating new molecules. One proposed mechanism is that cosmic rays convert carbon monoxide, which is common in interstellar ice, into carbon dioxide through a process called radiolysis,
a radiation-driven chemical reaction. Over time, the outer layers of the object would become enriched in carbon dioxide, forming an organic-rich crust that differs chemically from the object's interior. This cosmic ray processing hypothesis is appealing because it not only explains the high concentration of carbon dioxide, but also the unusual polarization we've observed. The crust would be made of complex organic molecules, carbon-rich grains and materials that scatter light differently than typical ice or silicate dust. When these grains are ejected into the coma, they produce the polarization signature we've observed.
It's a coherent story, one that connects the composition of the object to its long journey through interstellar space. But this hypothesis also raises questions. If 3IATLAS has spent millions or even billions of years traveling between stars, where did it come from originally? Every interstellar object has an origin, a star system where it formed, and a planetary disk where it condensed out of gas and dust. By studying the trajectory of 3IATLAS, astronomers have tried to trace its path backward to estimate where it came from. The results suggest that it didn't come from a nearby star system. Instead, it likely came from the general direction of the galactic center, or possibly from a region of active star formation hundreds of light years away. Pinpointing a specific origin is nearly impossible, but the implication is clear. This object has been wandering through space for a very long time, possibly since the early epochs of our galaxy, when star formation was more active and planetary systems were less stable. The composition of 3IATLAS also provides us with valuable insights into the diversity of planetary systems in the galaxy. If 3IATLAS formed around another star, its chemistry reflects the conditions of that system. The dominance of carbon dioxide suggests a colder, carbon-rich disk, one that might have formed from a molecular cloud with a higher metallicity or different isotopic ratios than our Sun's. This gives us a rare glimpse into alien geology, alien ice physics, and organic chemistry. Every measurement we make of this object adds to our understanding of how planets and comets form in other star systems. It expands our sample size beyond the single example of our own solar system, allowing us to better understand the diversity of cosmic conditions that exist out there. There's also a population question. If 3IATLAS represents a class of interstellar objects, bodies that have been processed by cosmic rays into organic-rich crusts with high carbon dioxide content, then there may be many more objects like it passing through our solar system undetected. Most would be too faint or too distant to spot, especially if they don't brighten significantly as they approach the sun. Our current detection methods are biased towards larger, more active objects. We're missing the smaller, darker, inactive ones. 3IATLAS might be the tip of the iceberg, the one bright example in a population of thousands or even millions that remain invisible to us. This has profound implications for how we think about interstellar material exchange in the galaxy. Stars don't exist in isolation. They form in clusters, migrate through the galactic disk, and gravitationally interact with each other. Over billions of years, objects get ejected from one star system and captured by another, or they simply drift through interstellar space, carrying with them the chemical fingerprints of their origins.
The galaxy is constantly shuffling its deck, mixing materials, exchanging building blocks. 3IATLAS is part of that process, a messenger from somewhere else, carrying information encoded in its atoms. The alien composition of 3IATLAS also points to more exotic interpretations. If this object is chemically so different from anything in our solar system, if its crust has been processed by cosmic rays into organic materials we don't fully understand, then perhaps its behavior near the sun is just as alien. Maybe the physics governing how it sublimates, how it releases gas, how it responds to solar heating is different from what we're used to. Perhaps we're applying models built for solar system comets to something that doesn't follow the same rules. Or, and this is where the speculation gets more uncomfortable, maybe the composition is deliberate. If you were designing an interstellar probe, You'd want materials that could survive the harsh environment of space for long durations. You'd want a crust that could shield against cosmic rays, that could self-repair or at least remain stable under radiation. You'd want volatiles that could be used as propellant, stored in stable ices that sublimate predictably near a star. Carbon dioxide fits that bill. It's dense, sublimates cleanly, and is easy to handle chemically. A carbon dioxide-rich composition might not be natural. It could be engineered. That's a stretch, certainly. There's no direct evidence suggesting the composition is artificial. But once you start seeing anomalies in one area, the behavior, it becomes harder to ignore anomalies in other areas, like the chemistry. These strange behaviors reinforce each other, building a case that something about 3-ATLAS is fundamentally different from what we expected. The cosmic ray processing idea remains the best natural explanation for the composition. It's solid, supported by physics, and testable. If we could sample the surface directly, analyze the organic crust in a lab, we could confirm or refute it. But that's not possible right now. We are stuck observing from millions of kilometers away, analyzing the surface through spectra, piecing together the clues. What's clear is that 3-ATLAS is chemically alien. Whether this alien nature comes from natural processes in a different stellar environment, from radiation exposure over eons, or from something more deliberate, we don't yet know. But the composition matters because it shapes how the object behaves, how it responds to the sun, and ultimately whether it breaks apart or survives intact. So, we've established that 3-ATLAS is chemically strange and behaviorally anomalous. The next question is physical. If it did break apart, how exactly would that happen? And what would the debris field look like? Let's now turn to the mechanics of fragmentation and the aftermath. Part 7. Fracture, dust, and debris fields. What could come next?
Breaking apart sounds simple, but the mechanics of it are anything but. A comet isn't a solid rock, it's a rubble pile, a loosely bound collection of smaller chunks, pebbles, and boulders, all glued together by gravity and held by weak mutual forces. The tensile strength, or the force required to pull the object apart, is low. You don't need much stress to overcome the cohesion. But you do need the right kind of stress in the right places at the right time. Solar heating is the first culprit. As 3-ATLAS fell toward the sun, the surface temperature rose dramatically. Ice on the day side began sublimating rapidly, turning directly from solid to gas. But this process isn't uniform. Some areas of the object might be darker, absorbing more heat, while other regions might be covered in dust that insulates the ice underneath. The result is differential heating, hot spots and cold spots that create internal stress. Ice expands and contracts with temperature changes. When these changes are rapid and uneven, cracks form. Then there's internal gas pressure. As the volatile materials sublimate beneath the surface, gas gets trapped under layers of dust and less volatile ice. Pressure builds up. Eventually, something gives. The crust ruptures and gas explodes outward, carrying dust and fragments with it. This is what causes the dramatic outbursts sometimes seen in comets. Sudden brightenings where a pocket of gas vents all at once. If enough gas builds up, if the structure is weak enough, the entire nucleus could shatter. Tidal forces from the sun add another layer of complexity. The sun's gravity pulls harder on the near side of the comet than the far side, creating a stretching effect. For large objects passing close to a massive body, the tidal gradient can be immense. This is what tore apart Shoemaker-Levy 9 near Jupiter. While 3-ATLAS passed perihelion at a distance of about 1.35 astronomical units, roughly 135 million kilometers from the sun, so the tidal forces aren't as extreme as they would be closer in, they still play a role, especially when combined with the internal stresses from heating and gas pressure. Rotation is also important. If 3-ATLAS was spinning, centrifugal force would push outward, adding additional stress. Comets can spin relatively fast, sometimes with periods of just a few hours.
If 3IATLAS was rotating and then began outgassing asymmetrically, the jets could act like tiny rocket engines, spinning the nucleus faster or altering its rotation axis. This would add even more mechanical stress and increase the potential for breakup. If fragmentation occurred, the pieces would initially stay relatively close together, perhaps only a few kilometers apart. However, the fragments would move at slightly different velocities based on their individual masses and the varying thrust from their own outgassing. Over time, the fragments would spread out along the orbit, forming a long, linear structure.
After weeks and months, this string of icy pearls would stretch out to millions of kilometers. Avi Loeb estimates that 3IATLAS could have fractured into at least 16 pieces. This estimate comes from trying to match the observed activity level to the required surface area. If the original nucleus was 5.6 kilometers across, its surface area was about 98 square kilometers. To get 16 times more surface area, you would need around 16 fragments of comparable size, or many more smaller ones. This provides a rough idea of the scale. This wasn't just a small crack, but a large-scale disintegration of the object. What would the debris field look like? As the fragments spread out, they would create a long trail of dust. Fragmentation exposes fresh surfaces, which sublimate more quickly and eject more dust. This dust would spread out under the influence of solar radiation pressure, forming a broad cloud along the object's orbit. The particles in this cloud would range from tiny, sub-micron grains to larger millimeter-sized pebbles. The smallest particles would be pushed farther away from the Sun, creating a fan-shaped distribution, while the larger ones would follow a path closer to the original orbit of the object. First, the good news. Earth's orbit is nowhere near 3IATLAS's trajectory, so we won't pass through its debris field. However, other spacecraft could. Satellites in high orbits, interplanetary probes, and solar observatories might encounter stray dust particles. The risk of damage is minimal, but not zero. A single grain of dust hitting a sensitive instrument at interplanetary speeds can cause significant damage. Mission planners are aware of this risk and are actively tracking the comet's trajectory and predicted debris distribution. There is also the potential interaction with the solar wind. Dust particles in space can become electrically charged due to ultraviolet light and collisions with plasma. Charged dust particles can interact with the solar wind, the stream of charged particles flowing out from the Sun. This interaction can create local disturbances in the magnetic fields, which may be measurable by instruments on spacecraft. Scientists studying space weather could notice anomalies in their data, little blips corresponding to the comet's passage. Visually from Earth, the debris field might not look like much. 3IATLAS is already faint, requiring powerful telescopes to observe it. If it fragments, each fragment might be even fainter, harder to track individually, or it could be lost in the overall brightness of the combined comet. However, the combined glow of the fragments could create intriguing effects, such as a stretched-out tail or multiple tail structures. Amateur astronomers with backyard telescopes have already been monitoring 3IATLAS, and some have reported seeing changes in its tail morphology, hints of complexity that could suggest fragmentation. The timeline for observations is crucial.
December 19, 2025, marks 3IATLAS's closest approach to Earth, about 90 million kilometers away, or 0.6 AU. This will be our best opportunity for high-resolution imaging and detailed characterization. If fragments exist, that's when we'll likely see them most clearly. If the nucleus is intact, we'll measure its size and shape with the highest accuracy. Telescopes worldwide are coordinating their observation campaigns, scheduling time, and preparing their instruments. This is a brief window, just a few days, when the geometry is optimal, and then the comet will continue its journey, fading into the distance. So Scenario A, the violent breakup, remains the most scientifically acceptable interpretation. It requires no new physics, no exotic explanations. It's just a comet undergoing the natural stress of solar heating and tidal forces. It's a straightforward hypothesis that explains the observations with the fewest assumptions. But even the simplest explanation isn't always the truth. Sometimes the reality is far stranger than the safe bet. What if 3IATLAS didn't break apart? What if it's still intact, and all the activity, those jets, the color shifts, the energy, are coming from something other than natural sublimation? That brings us to scenario B. Let's put it out there. The possibility that 3IATLAS might be artificial, a probe, an artifact, something built by someone else, is the elephant in the room. This idea is lurking beneath every anomaly, every unexplained data point. While mainstream scientists are careful, cautious, and reluctant to speculate without hard evidence, the speculation is happening anyway, on blogs, in preprints, at conferences, and in the public imagination. Avi Loeb has been one of the most prominent voices suggesting that we shouldn't rule out artificial origins. He's no fringe figure. Loeb is a tenured professor at Harvard, former chair of the astronomy department, and a respected theorist with hundreds of published papers. He's also willing to ask uncomfortable questions and push back against the scientific consensus when the data warrants it. With Oumuamua, where he suggested it might be a light sail, he made him a controversial figure. Some colleagues praised his willingness to think outside the box, while others criticized him for venturing too far into speculation and sensationalism. With 3IATLAS, Loeb is asking similar questions. In his blog posts, he has outlined a list of anomalies: the dominance of carbon dioxide, the energy budget problem where the required surface area exceeds the observed size, the non-gravitational acceleration that suggests propulsion rather than passive outgassing, the color shifts that hint at additional energy sources, and the statistical oddity of an object this large arriving from interstellar space. Each of these anomalies might have a natural explanation, but together they form a pattern that resists easy categorization.
Loeb has also pointed out the peculiar characteristics of 3IATLAS's trajectory. The object arrived on a retrograde orbit, moving opposite to the general direction of solar system bodies. While this is not impossible for a natural interstellar object, it is statistically less common. The orbit is also roughly aligned with the ecliptic plane, the flat disk where most planets orbit. Again, not impossible, but statistically less likely for a random interloper from the galaxy. If you were designing a probe to study a solar system, you might choose a trajectory that passes through the ecliptic, where most of the interesting stuff is. Loeb's interpretation of the energy signatures is also compelling. He suggests that the jets of 3IATLAS, with exhaust velocities in the range of 3 to 50 kilometers per second, look more like propulsion than sublimation. Ion thrusters used on spacecraft like Dawn and Deep Space One produce exhaust velocities in that range by accelerating ions with electric fields. Chemical rockets can do even better. If 3IATLAS is producing jets with velocities that high, and if its nucleus remains intact rather than fragmented, then we need to explain where this energy is coming from. Solar heating alone doesn't cut it. Loeb's bold hypothesis might be difficult for many to accept, but the data doesn't fit neatly into the natural comet model. He is pushing for a reconsideration of what we think we know about interstellar visitors and their origins. It's possible that 3IATLAS is just a strange comet, behaving in a way we don't fully understand yet. But it's also possible that we're looking at something entirely different, an interstellar probe or technological artifact from another civilization. If 3IATLAS is artificial, what would constitute strong evidence? Speculation is easy, but proof is difficult. What would we look for to definitively show that 3IATLAS is not a comet, but rather an artificial object? One of the most compelling signs would be a radio signal, a deliberate transmission in a narrow frequency band that cannot be explained by natural emissions would be the smoking gun. Scientists have already searched for signals from 3IATLAS using radio telescopes, but so far they've found nothing. However, the absence of evidence isn't necessarily evidence of absence. Perhaps the object is dormant or using frequencies or modulations that we don't monitor. Maybe it's designed to remain silent. Or perhaps it's just a rock and we're seeing patterns in the data where none exist. Optical signals would also be another potential clue. Deliberate flashes, pulses, or patterns in brightness that do not correlate with rotation or outgassing could suggest something beyond natural sublimation. So far, the brightness changes seen in 3IATLAS seem consistent with a rotating, asymmetrically active nucleus, but subtle patterns may be buried within the data, waiting for more careful analysis.
Trajectory maneuvers would be highly compelling. If the object changes course in a way that can't be explained by gravitational interactions or outgassing, it would be very hard to explain through natural processes. Monitoring the orbit of 3IATLAS over time will be crucial. Small deviations from the predicted path could be highly significant. If the object exhibits any subtle course corrections, that would push us even closer to the artificial hypothesis. Another important consideration is the question of intent. If 3IATLAS is an artificial object, why is it here? Is it simply passing through our solar system by chance, or is it here with purpose? Could it be an ancient, derelict probe, left over from a long-forgotten mission? Is it actively studying us, gathering data and sending information back to its creators? Or is it simply a piece of interstellar infrastructure, perhaps a navigation beacon, a warning system, or even something else entirely? The implications of this line of thinking are profound. If 3IATLAS is artificial, if it's technology, it means we are not alone. This would be humanity's first confirmed contact with an interstellar object created by another civilization. That realization would completely reshape our understanding of our place in the universe, how we view our future, and our relationship to the cosmos. Even though we don't have definitive proof yet, the possibility of artificial origins remains. It's something that can't be easily dismissed. What we observe in 3IATLAS is forcing us to consider questions we never thought we'd ask, and that alone is a monumental shift in how we approach the mysteries of space. There's no getting around it. The speculation surrounding 3IATLAS has captivated the public's imagination. Celebrities like Kim Kardashian have even weighed in, asking if the object could be aliens, and public figures like Joe Rogan have discussed it extensively on his podcast. These discussions, while entertaining, serve to amplify the story and draw more attention to it. The public fascination with 3IATLAS is real, and it is driving both funding and observation campaigns. However, it also puts pressure on the scientific community to deliver answers, sometimes pushing scientists to make conclusions faster than they would under normal circumstances. While the hype can generate interest and excitement in astronomy, it also risks sensationalizing the story and creating unrealistic expectations for what can be concluded from the available data. In the midst of all the excitement, it's important to remember that scientists are working to maintain credibility. They must be careful not to make claims they can't fully back up. The pressure for sensational headlines is high, but the responsibility of scientists is to present the facts, even when those facts lead to more questions than answers. Avi Loeb, who has been at the center of this debate, has faced his share of criticism. His suggestion that Oumuamua might be a light sail sparked controversy within the scientific community, leading some to accuse him of sensationalism. Yet his willingness to consider unconventional hypotheses has also made him one of the most prominent voices in the discussion of interstellar objects. Loeb continues to ask the questions that many others are hesitant to touch, challenging the scientific community to think beyond the conventional. As the story of 3IATLAS unfolds, the balance between public interest and scientific integrity will continue to be a delicate one. The scientific community must navigate the excitement and pressure from the public while staying true to the careful, methodical process that drives discovery. The reality is that science is often messy, filled with uncertainty, and sometimes requires years of analysis before any conclusions can be drawn. In the case of 3IATLAS, we're in the middle of this process. The data is still coming in, and the questions are still being asked. Whether the object turns out to be a comet, a fragment of a comet, or something entirely different, the journey to understand it will continue to push the boundaries of our knowledge. 3IATLAS, whether it's a comet or something else entirely, is more than just an astronomical discovery. It forces us to confront the unknown in a way that is both humbling and exhilarating. Our current understanding of the cosmos is being challenged by an object from beyond our solar system. What does this mean for the future of space exploration? As we continue to study 3IATLAS, we must also consider the larger implications of this discovery. The fact that an object like 3IATLAS could come from interstellar space tells us something profound about the nature of the galaxy. It suggests that the universe is not static and that material and objects constantly move between star systems. If 3IATLAS represents a class of interstellar objects that are more common than we currently understand, it could reshape our views of our solar system, its formation, and its place in the galaxy. More than that, it raises the existential question of whether we are alone. If 3IATLAS is not a comet but a technological artifact, then we must confront the possibility that there is other intelligent life in the galaxy. It would change everything, from the way we view ourselves to how we approach the search for extraterrestrial life. But even if 3IATLAS turns out to be just an unusually strange comet, the story still matters. It forces us to reevaluate our understanding of comets, the materials they contain, and the processes that govern their behavior. It reminds us that the universe is full of surprises, and every new discovery offers the opportunity to expand our knowledge.
3IATLAS has given us something truly unique, a chance to explore the unknown, to push the limits of our knowledge, and to entertain ideas that we might have dismissed just a few years ago. Whether it is a comet, a fragment of a comet, or something entirely different, it has already succeeded in challenging our assumptions. It has forced us to think about the galaxy in a different way. In many ways, the discovery of 3IATLAS is a cosmic invitation. It's an invitation to re-examine our place in the universe, to consider what lies beyond our solar system, and to confront the possibility of interstellar exploration. It's easy to look at objects in our solar system and think we have it all figured out. We've mapped the planets, cataloged the moons, and sent probes to the farthest reaches of our system. But when something like 3IATLAS arrives from the farthest reaches of interstellar space, it reminds us that there is so much more out there that we still don't understand. Imagine for a moment if we were to build the technology capable of sending missions to interstellar space to explore objects like 3IATLAS in person. It would be a monumental leap in human achievement. This is the kind of challenge that drives the human spirit, the desire to go beyond what we know and discover what lies in the unknown. Whether it's a probe sent to collect samples or a long-range telescope designed to observe distant visitors like 3IATLAS, the pursuit of knowledge never ends. But even as we grapple with the mystery of 3IATLAS, we must keep our focus on the bigger picture. The questions raised by this object go beyond just our understanding of comets. They challenge the very foundation of how we approach exploration, discovery, and the search for life. In this context, 3IATLAS becomes more than just an astronomical curiosity. It becomes a symbol of our desire to reach out into the cosmos and understand our place within it. While our current technology may not allow us to reach these interstellar objects in person, the path toward such exploration is slowly taking shape. Organizations like NASA, ESA, and private space companies are already looking toward the stars with missions like Breakthrough Starshot, which aims to send tiny probes to nearby stars within a generation. These efforts might seem distant now, but each breakthrough in space technology,
Each new discovery brings us closer to the moment when interstellar exploration will be within our grasp. 3IATLAS is just one step in that direction, proof that, even in the vast emptiness of space, we are not as alone as we once thought. In the end, whether we ever find the definitive answer about the origins of 3IATLAS doesn't change the fundamental truth. This object has already expanded our horizons.
Its strange behavior, its mysterious composition, and its interstellar origins have forced us to think outside the box, to challenge our assumptions, and to imagine a future where humanity explores the stars. It is a reminder that, in science, as in life, the most exciting discoveries often come from the most unexpected sources. 3IATLAS has given us a glimpse of the unknown, and it's up to us to keep looking, to keep asking questions, and to continue pushing the boundaries of what we know. The universe is vast, and the mysteries it holds are waiting to be uncovered. As we reflect on 3IATLAS and its role in expanding our understanding of the cosmos, we must also consider the broader implications for interstellar exploration. Although humanity has yet to send a probe outside of our solar system, efforts are already underway to make this a reality. Missions like the recently proposed Breakthrough Starshot initiative aim to send tiny spacecraft to the closest stars at a fraction of the speed of light, with the potential to reach interstellar space in a matter of decades. Such missions may be the next logical step in human space exploration, and 3IATLAS has provided a compelling motivation for us to push forward with these efforts. By studying interstellar objects like 3IATLAS, we can gain critical insights into the conditions of space beyond our solar system and the materials that exist in other star systems. These insights could provide valuable clues about the potential for life elsewhere in the universe, the resources available to future explorers, and the overall structure of our galaxy. In addition to expanding our scientific knowledge, the exploration of interstellar space also raises important philosophical and existential questions. If we were to find evidence of advanced alien technology, or even just trace the path of interstellar objects like 3IATLAS, it would forever change how we view our place in the universe. The prospect of encountering intelligent life, or even just discovering the remnants of an ancient civilization, is both exciting and humbling. These possibilities are still far in the future, but 3IATLAS has brought us one step closer to realizing them. The discovery of an interstellar object like 3IATLAS has opened our eyes to the vastness of the galaxy and the potential for interstellar travel. It has made us aware that, just beyond our own solar system, there are worlds to explore, mysteries to solve, and a whole universe waiting to be understood. In the coming years, as our technology continues to advance, we may look back at 3IATLAS as the moment when interstellar exploration began to shift from science fiction to reality. Whether we are able to send missions to distant stars in our lifetimes or not, the knowledge and curiosity sparked by this object will continue to drive the search for answers and fuel the desire to explore the unknown.
3IATLAS may not hold the answers we hoped for, but it has opened a new chapter in space exploration. It has challenged our assumptions about what we know and what we still have left to discover. It has pushed the boundaries of our understanding and forced us to confront the possibility that there is more to the universe than we ever imagined. As we continue to study this enigmatic object and others like it, we must remain open to new possibilities. Science thrives on curiosity, and the discovery of 3IATLAS is a perfect example of how unexpected events can lead to new ideas and breakthroughs. Whether 3IATLAS is a comet, a fragment of a comet, or an artificial object, it has provided us with an incredible opportunity to rethink our place in the universe. The journey to uncover the mysteries of 3IATLAS is only just beginning. As more data comes in and more telescopes turn their attention to the object, we may uncover even more surprises. But no matter what we find, we can be certain of one thing: The pursuit of knowledge will continue to propel us forward into the great unknown, pushing the limits of what we thought was possible and opening new doors to the universe. As we stand on the precipice of discovery, the question of extraterrestrial intelligence looms larger than ever before. 3IATLAS has given us more than just a puzzling anomaly in our solar system. It has rekindled the debate about the possibility of intelligent life beyond Earth. If 3IATLAS is an artificial object, a probe from another civilization, it would not just be a monumental scientific discovery, it would mark the beginning of an entirely new chapter in humanity's understanding of its place in the universe. The search for extraterrestrial intelligence, SETI, would take on an entirely new meaning. Historically, the search for extraterrestrial intelligence has been rooted in the assumption that any alien signals or objects we encounter would be similar to those produced by us – radio waves, electronic signals, or visible light emissions. However, 3IATLAS, with its peculiar behavior and mysterious composition, challenges that assumption. The object's strange acceleration and outgassing patterns, as well as its composition, suggest that there may be more ways for extraterrestrial civilizations to communicate or interact with their surroundings than we ever imagined. If 3IATLAS is indeed an artificial object, it would be a wake-up call for the scientific community. We have spent decades listening for alien radio signals, scanning the skies for patterns that indicate intelligent life. But what if they don't communicate the way we do? What if they use entirely different methods to propel themselves across the galaxy, to explore, to observe? The discovery of a technological artifact from beyond our solar system would open up entirely new avenues for SETI research, ones that we are only beginning to explore.
SETI has largely focused on the search for signals from distant civilizations. Projects like the Search for Extraterrestrial Intelligence at the Allen Telescope Array, which listens for narrow-band radio signals, and the Breakthrough Listen Initiative, which aims to scan the entire sky for potential alien communications, have been the backbone of this search. These efforts are still ongoing, and they have yet to yield definitive proof of extraterrestrial life. But the discovery of 3IATLAS changes the narrative. Suddenly, the search for alien life is not just about receiving signals, it's about encountering alien artifacts, objects traveling across space, just as 3IATLAS has done. If we look at the object through the lens of SETI, we must begin to ask, what else might be out there, hidden in plain sight? What if we've been looking for the wrong kind of signal all this time? The discovery of 3IATLAS forces us to reconsider how we search for alien civilizations, and it challenges us to think beyond traditional paradigms. The universe is vast, and we've only begun to scratch the surface of what might be out there waiting to be discovered. If 3IATLAS is indeed an artificial object, the next big question is, how could such an object be built, and what would its purpose be? If we accept the possibility of intelligent civilizations capable of sending probes across interstellar distances, we must begin to consider the technologies required to accomplish such feats. The distances involved are staggering, and the energy required to travel between stars is immense. One concept that has been widely discussed in the realm of science fiction is the idea of light sails. Thin, reflective materials that could be propelled by radiation pressure from a star. These sails could be incredibly lightweight, allowing them to accelerate over vast distances using nothing more than the energy from starlight. Such technology could, in theory, allow a probe to travel interstellar distances. The idea of using light sails for interstellar travel has been explored in various scientific studies, and even real-world projects like Breakthrough Starshot aim to develop such technologies. However, building a functional light sail that could survive the harsh conditions of space, cosmic radiation, dust, and micrometeorites would require advanced materials and an unprecedented level of precision engineering. Another possibility is the use of ion propulsion systems. These systems are already used in spacecraft within our solar system, such as NASA's Dawn mission.
Ion thrusters work by using electricity to ionize a propellant, which is then accelerated through an electric field to produce thrust. While ion propulsion systems are currently limited in terms of the thrust they can generate, they're incredibly efficient and could potentially allow for long-duration space travel at high speeds.
For an object like 3IATLAS, an ion propulsion system could be used to gradually accelerate over long periods, providing a steady and controlled source of propulsion. This technology is already on the drawing board, and it might not be far-fetched to imagine that an advanced civilization could use it for interstellar travel. But let's go further into speculative territory. What if 3IATLAS is a type of self-replicating probe, an autonomous craft designed to explore the galaxy and harvest resources along the way? We are beginning to explore the concept of self-replicating machines here on Earth, though we are still far from being able to create them. Such machines would be capable of constructing copies of themselves using local materials, allowing them to spread across the galaxy and explore planets, moons, and asteroids. If 3IATLAS is part of such a system, it might be just one of many probes sent out by an alien civilization to investigate the universe. This concept, known as von Neumann probes, is a fascinating idea that has been discussed in the context of extraterrestrial life and advanced civilizations. If 3IATLAS is a von Neumann probe, it would be capable of constructing new probes to send out across the stars, perpetuating its mission indefinitely. However, while these ideas are fascinating, there is currently no direct evidence to suggest that 3IATLAS is anything more than a natural object. It's still possible that this strange object is simply a comet, a highly unusual comet to be sure, but still a comet nonetheless. As we continue to gather data from telescopes and observatories, we will have a clearer picture of its nature. If further analysis reveals that the object behaves in ways consistent with artificial technology, it would mark a monumental shift in our understanding of the universe and our place within it. The potential discovery of extraterrestrial artifacts such as 3IATLAS would have profound and far-reaching implications not just for science but for humanity as a whole. The mere suggestion that an advanced civilization might have left traces of its technology, whether in the form of probes, artifacts, or other objects, would fundamentally change our worldview. The discovery of a technological object from another star system would signal a moment in history akin to the first confirmation of extraterrestrial life, only on a far more tangible and direct level. First and foremost, it would challenge our assumptions about the uniqueness of life on Earth. For centuries, humans have grappled with the idea that we are alone in the universe, a thought that permeates our religions, philosophies, and even our search for meaning. The discovery of an artificial object from another civilization would shatter the notion that Earth is the only cradle of life and intelligence. This realization could alter the course of human history in ways we can hardly predict.
The social and psychological impact would be enormous. For some, it would be an awe-inspiring confirmation that life, and possibly intelligent life, exists elsewhere. For others, it could be unsettling or even terrifying, as it forces us to confront our vulnerability in a vast, populated universe. The implications for society would be complex, raising questions about how we relate to other life forms, how we approach our place in the cosmos, and what responsibilities we may have in this new reality. From a scientific perspective, the discovery of extraterrestrial technology would open up entirely new fields of research. It would force us to reevaluate our understanding of physics, engineering, and biology. How could a civilization develop the technology to send probes across the vast distances of interstellar space? What kind of materials would they use? How would they power their machines? And how would those machines survive the harsh conditions of space over millennia? Such questions would require new approaches, new tools, and perhaps entirely new scientific paradigms. The study of interstellar objects like 3IATLAS could catalyze a new era of discovery,
as we learn from the technology and materials left behind by extraterrestrial explorers. Moreover, the discovery would spark a new race in science and space exploration. Governments, private enterprises, and scientific institutions around the world would likely accelerate their efforts to explore space, driven by the desire to understand and possibly replicate or reverse engineer the technologies of alien civilizations. The international scientific community would undoubtedly collaborate on unprecedented scales, sharing data, resources, and knowledge to solve one of the greatest mysteries in human history. Beyond the realm of science, this discovery could also ignite new philosophical and ethical debates. If we find proof of extraterrestrial technology, it will likely raise questions about how humanity should respond. Should we attempt to contact these civilizations? What if they are more advanced than we are? How would we interact with them? The question of whether to actively seek out other civilizations or whether we should adopt a more cautious approach would become a central issue in future discussions about space exploration. In the absence of direct contact, we might still begin to think about what kind of messages or signals these civilizations might be sending. What if we are not meant to interpret their objects in the same way we interpret our own technologies? What if these artifacts are meant as a kind of cosmic message, an invitation to future generations of intelligent life to come and discover the wonders of the universe? These questions go far beyond the technical details of how to reach other star systems. They delve into deep philosophical inquiries about the nature of life, intelligence, and our place in the cosmos.
The possibility that we are not alone in the universe and that other civilizations have been out there for much longer than we have raises profound questions about what we might learn from these civilizations and how we can grow as a species. 3IATLAS, whether it turns out to be a comet or a probe, represents a pivotal moment in the history of space exploration. The discovery of interstellar objects like this one brings us closer to the ultimate frontier, the exploration of the stars. But are we ready for this next great leap? Despite the remarkable achievements of the past few decades, such as landing rovers on Mars, sending probes like Voyager 1 and 2 into interstellar space, and achieving extraordinary feats of satellite technology, we are still in the infancy of space exploration. Our current methods of propulsion and space travel are limited, and the distances involved in reaching other star systems are staggering. Even with the theoretical development of advanced propulsion systems like ion thrusters, nuclear fusion drives, or even concepts like the Alcubierre drive, interstellar travel remains well beyond our current capabilities. However, the discovery of 3IATLAS has the potential to accelerate the development of space exploration technology. It has already sparked renewed interest in projects like Breakthrough Starshot, which aims to send small, lightweight spacecraft to Alpha Centauri, our closest star system, within the next few decades. Although these efforts are still in their early stages, the idea of reaching other star systems is now within the realm of possibility. The discovery of interstellar objects like 3IATLAS could serve as a catalyst for investment in the technology and infrastructure required to achieve interstellar travel. The future of space exploration will also require international collaboration. No single nation or organization can bear the burden of exploring the stars alone. The technological challenges are too great, the costs too high, and the risks too immense. We need a global effort to pool resources, share knowledge, and work together in the pursuit of interstellar exploration. This may involve partnerships between governmental space agencies like NASA, ESA, and Roscosmos, as well as private companies like SpaceX and Blue Origin,
which are already pushing the boundaries of space travel. But perhaps the most important aspect of this future exploration will be the change in mindset it will require. As we continue to study objects like 3IATLAS, we need to embrace the unknown, take risks, and venture into the vastness of space with the same sense of wonder and curiosity that has driven humanity's exploration of Earth's oceans, skies, and frontiers. The pursuit of knowledge and the desire to understand our place in the cosmos should be the driving forces behind every mission, every breakthrough, and every discovery.
The future of space exploration is not just about reaching new worlds, it's about expanding our understanding of who we are as a species and what our potential might be in the broader universe. With the discovery of 3IATLAS, humanity has been given a glimpse of a vast, unexplored frontier. The question now is, are we ready to take the next step? As we look to the future of space exploration, it's impossible to ignore the immense role that technology will play in shaping our destiny. While the question of extraterrestrial intelligence continues to captivate the human imagination, the technology required to explore the universe, interstellar travel in particular, will evolve in ways we can't yet fully predict. However, we are already witnessing the early stages of that evolution, and 3IATLAS might be the trigger that accelerates it. The idea of traveling between stars is no longer confined to science fiction. The development of faster propulsion technologies, such as ion engines, nuclear propulsion, and theoretical concepts like the warp drive, are becoming serious areas of study within the scientific community. Each of these technologies has its own set of challenges, but all offer potential pathways to interstellar exploration. The issue of propulsion is central to this conversation. Current space travel methods rely on chemical propulsion, which, although effective for missions within our solar system, is far too slow for interstellar travel. Even the fastest spacecraft ever built, like NASA's Parker Solar Probe, which travels at speeds up to 700,000 kilometers per hour, would take over 17,000 years to reach Alpha Centauri, our closest stellar neighbor. Clearly, this method is not sufficient for interstellar exploration. One promising solution is ion propulsion, which has already been used in missions like NASA's Dawn spacecraft. Ion engines work by ionizing a propellant, usually xenon, and then using electric fields to accelerate the ions to high speeds, generating thrust. While this method provides far greater efficiency than chemical rockets, the amount of thrust it generates is still very small. This makes ion propulsion suitable for long-duration missions within our solar system, but it's still far from practical for sending missions to distant stars.
The idea of using nuclear fusion or even antimatter propulsion, though still speculative, has captured the imagination of many scientists. Fusion propulsion would harness the power of nuclear fusion, the same process that powers stars, to provide near-light-speed travel. Antimatter propulsion, while theoretically possible, remains far beyond our current technological capabilities, but offers the potential for highly efficient and fast interstellar travel. These technologies, if they can be developed, would open up the possibility of exploring distant star systems in a matter of decades or centuries rather than millennia. But it's not just the propulsion technology that will need to evolve. Spacecraft design, energy systems, and life support mechanisms will also need to be rethought. A mission to another star would likely take decades, if not centuries, so long-term sustainability will be a key consideration. Spacecraft will need to be self-sufficient, capable of recycling air and water, growing food, and maintaining life support systems over long periods. Advances in artificial intelligence and robotics will be essential for monitoring spacecraft systems, conducting scientific experiments, and managing resources.
Interstellar travel will require a collaborative global effort, bringing together resources and expertise from governments, private companies, and academic institutions around the world. But just as important is the mindset shift that will accompany these advancements. The pursuit of interstellar exploration is not simply a technological challenge, it is a philosophical one. It forces us to consider questions about the human condition, the future of our species, and our role in the universe. As we continue to study objects like 3IATLAS, we are reminded of the vastness of the universe and the incredible possibilities that await us. Whether or not we encounter extraterrestrial artifacts or civilizations, the drive to explore and understand the cosmos will continue to shape humanity's future. The possibility of interstellar exploration opens up not only a future full of technological advancements, but also a profound philosophical journey for humanity. If we continue down this path of discovery, what will it mean for us as a species? What are the ethical, existential, and societal implications of sending humans or machines to other star systems? The fundamental questions about our place in the universe have always been part of human philosophy, from the ancient Greeks to the modern day. As we venture beyond our solar system, these questions will only intensify. How do we define life in a truly cosmic sense? Are we ready to meet other intelligent civilizations? And if so, how would we communicate with them? There are also significant ethical concerns that will arise as humanity ventures deeper into the cosmos. If we discover evidence of intelligent life, how will we react?
Should we try to communicate with them, or should we remain silent and avoid disturbing their development, as the prime directive in science fiction suggests? How do we navigate the risks of potentially contaminating other worlds with Earth-based life, or vice versa? These are issues that have been raised by astrobiologists, ethicists, and futurists for years, but as interstellar exploration moves closer to reality, these questions will become even more pressing. The discovery of extraterrestrial life, whether microbial or intelligent, would also force us to rethink our own existence. What does it mean to be human if we are not the only intelligent beings in the universe? If there are other civilizations out there, what does that say about the likelihood of life elsewhere and the possibility that we are just one in a vast galaxy of life forms? These questions challenge us to reflect on the meaning of life itself, our responsibilities to each other and to the rest of the universe, and our place in the grand cosmic story. Perhaps most importantly, the quest for interstellar exploration forces us to confront the ultimate question: what is the purpose of human existence in an ever-expanding universe? For much of history, humanity has looked inward, focusing on our own survival, development, and progress. But the more we learn about the universe, the more we realize that our story is part of something much larger, an intricate, interconnected cosmos that has been unfolding for billions of years. Interstellar exploration is a quest not just for new frontiers, but for understanding the deeper meaning of life itself. As humanity pushes further into the depths of space, one thing becomes clear: interstellar exploration is not just about discovering new worlds or reaching distant stars. It's about uniting the human race in a shared vision of exploration, discovery, and understanding. It's about coming together as a species to tackle the greatest challenges ever faced and to work towards a common goal: understanding the universe and our place within it. The vision of a unified future is critical as we embark on these long-term, ambitious projects. Space exploration has the power to transcend national borders and political divisions. While the exploration of space has often been the domain of powerful nations, the future of interstellar exploration will require a more collaborative and collective approach. No single nation or organization can conquer the challenges of interstellar travel alone. It will require cooperation on an unprecedented scale across countries, cultures, and industries.
From spacecraft design to propulsion systems, from artificial intelligence to sustainable life support, the technologies needed to make interstellar travel a reality will require the best minds and the most innovative thinkers working together. In addition to the scientific and technological collaboration, the philosophical and cultural aspects of this mission will need to be considered. As we venture beyond our solar system, we will encounter not only new celestial bodies, but also new ways of thinking about our existence. Interstellar exploration represents a journey of self-discovery, as we seek answers to questions about the nature of life, consciousness, and intelligence. It challenges our assumptions about the uniqueness of humanity and our role in the cosmos. The discovery of 3IATLAS has already sparked a shift in our thinking about the universe. It's a reminder that we are not alone in our curiosity about the cosmos. It reminds us that the quest for knowledge is a fundamental part of who we are as human beings. Whether or not 3IATLAS is an artificial object, it has inspired us to think more deeply about the possibilities of life beyond Earth and the future of exploration. This collective vision for the future, one that includes humanity as a whole, working together in pursuit of a common goal, is what will make interstellar exploration possible. As we develop the technologies, methodologies, and philosophies necessary for long-term space exploration, we must also ensure that the journey is a shared one. It's not just about reaching new stars. It's about creating a future where every human being has the opportunity to participate in the grand adventure of discovery. The lessons we learn along the way about collaboration, perseverance, and humility will not only help us reach the stars, but will also make us better stewards of our own planet. The challenges of space exploration are inherently connected to the challenges we face here on Earth. The technologies we develop to explore the stars can be used to address the pressing issues facing our world: climate change, resource scarcity, and sustainability. As we reach for the stars, we must not forget to take care of our home. 3IATLAS and the ongoing exploration of interstellar space will leave behind a legacy of discovery, a legacy that will continue to inspire future generations to reach for the stars. It will be a legacy of questions asked, mysteries solved, and new possibilities revealed. The legacy of 3IATLAS, whether it turns out to be a comet, an artificial probe, or something else entirely, will be the beginning of a new chapter in the story of humanity's journey through the cosmos. For now, we can only speculate about what 3IATLAS is, what it represents, and what it might mean for the future of space exploration. But the fact that it has captured our imagination and challenged our understanding of the universe is in itself a remarkable achievement. It has opened the door to new possibilities, to new questions, and to a future that we are only beginning to explore. As we look to the stars, let us remember that the pursuit of knowledge is a journey without end. Whether we find answers to the questions posed by 3IATLAS or not, the quest to understand the universe will continue. It will continue because it is part of what it means to be human, the drive to explore, to learn, and to grow. And as we reach for the stars, we will carry with us the legacy of 3IATLAS, a reminder that the universe is full of mysteries waiting to be uncovered, and that our journey has only just begun.